The efficient design of big steel transfer truss structures can be very hard as an engineer, and you quite often just want to throw additional steel at it instead of trying to achieve the efficient design that we should be aiming for. There's a new innovative approach that allows you to achieve both the structural efficiencies and design safeties that every engineer wants to see. So let's find out about it. My name is Brendan, your structural engineer. Now let's get into it. As structural engineers, it is important that we understand what disproportionate collapse is and why we need to design for it. But what does it actually mean? It means that you can't have one single element fail and then have disproportionate amount of damage spread out through the whole building. For example, if you lose one column, you can't lose the whole structure. Now you may lose the floor above it, but not everything else above that point. And there's been countless facts throughout history where we've seen progressive collapse lead to disastrous approaches. So it's prudent that all engineers make sure they're detailing their structures such in a way that they can't have a catastrophic collapse from a single element failure. The Eurocode provides us some guidance on how we can design for this risk-based approach to make sure we don't have a catastrophic failure within our structure. And this is from a simple design curve from the ASIC, which has a force deflection diagram. So you go your first point, which is that vertical point, and you come to your immediate occupancy level. So it still means that you're within static and standard design ratios. As you push the forces a little bit further, you move into the area where you can see your life safety. So making sure the structure is still safe for everyone and the occupancies within it. But it means that you might need to repair some of the damage. So you push past the point where you can just move back into the building, but you need to repair it before everyone moves in. But after you get past this point is where you see more of a non-linear behavior, as a little bit of force leads to a great movement. And that's where we move up to the next point, which is collapse prevention, which is meaning that we don't want the whole building to come crashing down on us. Now that's really the critical point, as we don't want to push past that point, because if that point fails, we lose the whole structure. By knowing these 3 points, we can apply this back to our steel design for that more efficient approach. So by being able to analyzing the structure and seeing about how much damage has occurred and is it a catastrophic failure or not, we can assess the structure if it's going to collapse underneath the forces that applies to it. Now this will mean that we'll need to apply a simple non-linear behavior where if we exceed a certain force, we lose certain elements, which can lead to a cascading event and the whole building coming down. But it does mean we need to meticulously go through the design and find each point and see if we lose this element, what is the knock-on effects and where does the forces get redistributed to? Well, first up, when we're starting this risk-based approach, we need to look at the element that we're designing for. If we lose this element as a whole, will it lead to a catastrophic failure? If the answer is no, it means that it doesn't really have any additional complexities that we need to look for, and we can just move on. If it does say yes, it means that we need to approach it in a more systematic way. Now this is where you'll build your model in an FEA analysis, and that's where you'll be able to play with it and see what happens when you delete specific elements. Now again, this is not just your standard elastic analysis, as you can push elements beyond their real stress points. So it needs to be a non-linear system, or you need to have some way of making an iterative non-linear system where you push it to a certain point, pull out an element and reassess until the structure has led to a stable state. So first up, you build your model in ETABS. You choose one of those elements to be removed and look on the knock-on effects of that system. So you're saying, what elements get stressed? Where does the load redistribute to? So we'll be able to remove specific elements when it exceeds its critical force, and also allow for additional rotation once it's gone beyond the life safety situation. And this is where we go into a cyclic range of assessing these different elements, where we go up and we remove that one element, see where the forces go. Has it exceeded all the lateral forces, or do we need to size up certain elements? And we just keep cycling until we removed each element, and after which we can identify which areas need to be strengthened, which areas are okay as is, so they're in that life safety situation. Oh yes, this is something that you could have done in the past, but it would have taken a long time, lots of hand computations, sorting out which ones fails, slowly removing, rerunning that analysis. And with the rise of computers, things started to get faster. I have done this type of approach which would require that manual sorting and moved it to an Excel spreadsheet. It wasn't for this exact situation, but it still applies through that computational requirement. That Excel spreadsheet is not very efficient. So when I ran that Excel spreadsheet, it could take upwards of 18 hours to sort all the data and make that analysis work. Now, what I did was jump into a little program called Python, and I was able to sort that same data that took hours in the matter of seconds to thoroughly analyze if we lose one or two different members and see what the knock-on effects of the structure are to make sure it doesn't have a catastrophic failure. So when we're really thinking about design efficiency and life safety, it's not something that has to be in separate hands with each other. We can achieve both of them through efficient and more complex design solutions. If you want to learn more about the detailed design of steel connections, I've got a perfect video here that you can watch. And if you're interested in supporting the channel, there's two ways that you can do this. There's either links in my below description to my Patreon page, or you can become a YouTube member. Without the support of my YouTube members or Patrons, this type of content would not be possible. As always, stay safe, keep learning, and I'll see you next week. Bye.